In this video, we're going to talk about the area of a parallelogram in R3. So suppose that we have two vectors A and B in R3. Okay, here's my vector A, and here's my vector B. Now these two vectors are going to form a parallelogram like this. And the question is, what's the area of this parallelogram? Well, there's a formula for the area of a parallelogram, which is the base times the height. So we would take this length and multiply it by the height, which is this length, the height of the perpendicular line segment from one of the vertices down to the base. So we need to figure out what those lengths are. Well, the base of the parallelogram is the magnitude of the vector A, right? It's the length of this base vector A. And for the height, well, we want this blue length, and you have this vector. You have this vector B, and A and B make an angle theta, and so the height is going to be this length. This length is going to be the magnitude of B times the magnitude of cosine of theta. The reason I put magnitude is because cosine of theta might be negative. If theta, in this picture I drew the parallelogram so that A and B make an acute angle, but they could make an obtuse angle, and then cosine would be negative, but you still have that the height would be the magnitude of B times the absolute value of cosine of theta. So that's the height of this parallelogram, and therefore the area is the product of the base and the height. That's just the formula for the area of the parallelogram, and when you put that together, you get this number. So I just want to emphasize that we have these vertical bars, but the vertical bars have a different meaning. So here we have the magnitude of A times the magnitude of B, right? That's the length of A times the length of B. And then it's being multiplied by the absolute value of cosine of theta. Well, we can actually find different ways of rewriting this quantity in terms of the dot product and the cross product. And to see how we can do that, let's square this quantity, the area of the parallelogram. If you square it, you just get the magnitude of A squared times the magnitude of B squared times cosine squared of theta. And because cosine squared of theta, so let's just recall that cosine squared of theta is equal to 1 minus sine squared of theta. Okay, so if you multiply both sides by the magnitude of A squared times the magnitude of B squared, and you distribute that, then you're going to get this quantity here. And the magnitude of A squared and the magnitude of B squared is just A dot A and B dot B. So I just rewrote this. And then A dot B, remember that A dot B is the magnitude of A times the magnitude of B times let's see, hold on. Oh, I made a mistake. This should be sine. Oops. Okay, wow. This should be sine. Okay, so this should be sine squared, and this should be cosine squared. Okay, now it's correct. Sorry. Oh, wow, I even made a mistake here, too. Okay, let me go back. Magnitude of sine theta, right? Like that. Okay, so now it's correct. So the a dot b is the magnitude of a times the magnitude of b times cosine of theta. And so when you square this, you get the magnitude of a squared times the magnitude of b squared times cosine squared of theta. Okay. So you get this expression in the asterisk. Now it turns out that that's equal to what you get if you take the cross product of a and b, so a cross b, and then you take the magnitude and you square it. I'm not going to write out the details of this. It's kind of messy algebra, but it's not that hard. You just write down the vector components of a and b. So the vector a is just a1, a2, a3, and then b is b1, b2, b3, and then you just write out everything in terms of those components, and you can check that they're the same. So that's what I wrote, messy algebra. And therefore, so this was the square of the area of the parallelogram, and so therefore the area of the parallelogram is the magnitude of the cross product. So that proves the fact that if you have two vectors a and b, and you want to know the area of the parallelogram, it's the magnitude of a cross b. Now notice that this starred expression here is equal to the determinant of this matrix, this 2 by 2 matrix, where the entries are a dot a dot b, b dot a, and b dot b. And just for clarity, a dot b is the same as it's the same as b dot a. Okay. But when it's written like this, you can see that this 2 by 2 matrix, this matrix is the same as the product of these two matrices, where you have the first matrix where the rows are a and b, and then the second matrix is the matrix with columns a and b. Well, if you define A to be the matrix whose columns are a and b, that's just A transpose times A. And so what we found is that this starred quantity is the same as the determinant of A transpose A. And so the area of the parallelogram is the square root of the determinant of A transpose A. So that is another way of expressing the area of the parallelogram. And by the way, you can do the same thing if you have two vectors in R2, because if you have two vectors in R2, so let's say you have A and, I don't know, let's say this is B. Well, you can think of these as, so if this is an R2, if your first vector is A1, A2, and your second vector B is B1, B2, and you get this parallelogram, and you want to find the area, you can actually look at the corresponding picture in R3, where you have the x-axis, the y-axis, positive x, y, and z, and you just look at a1, a2, 0, and b1, b2, 0. Right? These are two vectors in R3, and you have the same thing. And what would be the magnitude of the cross product? Well, it would be, so you have the magnitude of A cross B, and for A cross B, we have this kind of mnemonic, right? Like this. Well, A is A1, A2, 0, and B is B1, B2, 0. And when you take the cross product, you'll see that this is K hat times A1, B2 minus A2, B1. And so the magnitude is equal to the absolute value of A1, B2 minus A2, B1. So that's the determinant of this matrix. Where the columns are the vectors A and B. So this 2 by 2 determinant is the same as the area of the parallelogram. Well, it's the absolute value of the determinant. Sorry, it should be the absolute value of the determinant, right? Because the determinant itself might be negative. Okay, so that's the area of the parallelogram in R2. It's the area of this parallelogram. So this has area, the absolute value of A1, B2 minus A2, B1. Which, if you think about it, is still the square root of the determinant of A transpose A. So if you call this matrix A, okay, A transpose A, the determinant of A transpose A is the same as the determinant of A transpose times the determinant of A. So here we're using the fact that A is a square matrix. It's a 2 by 2 matrix. And the determinant of A transpose is the same as the determinant of A. That's a property of determinants. So you have the determinant of A times the determinant of A. That's the determinant of A in parentheses squared. So the square root of the determinant of A transpose A is the square root of the determinant of A squared. Well, if you take a number and you square it and then take the square root, you took the absolute value. So it's the absolute value of the determinant of A. So this square root of the determinant of A transpose A shows up in both cases. Now notice that in this case, A, right, in the first example, your matrix A is not square. So you can't split up the determinant of A transpose A as the determinant of A transpose times the determinant of A, because your matrix A here is a 3 by 2 matrix, right? Because A and B are vectors in R3. When you have this matrix here, you have a 2 by 2 matrix. Okay, so that's what I want to say about the area of a parallelogram in R3.